let's try this one. So you have a triangle with center O. And then we draw the angle bisectors. And they meet at I. So AD, BE, and CF. MN and P are on EF, P, and DE. They're the midpoints. Oh no, they're not the midpoints. They're basically you draw the perpendiculars. This should be the other one. So it should be M. All right. Looks like Serdar is joining. Hey Serdar, thanks for joining.
Hi.
So we solved two problems, and then one we kind of got stuck on, and now we're just starting this one. So this IN, this should be N, and this should be P. And we want to show AM, BN, and CP. First of all, we want to show they concur. And then once we show they concur, we want to show it lies on OI. All right. Let's draw these points too. All right. So then I'm going to hide a bunch of stuff. Actually, let me hide almost everything. So I have this, 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 and this. All right. And we want to show AM. First of all, we want to show AM, BN, and CP concur. That's step one. So let's see if that's true. Yes, it is. And then it does look like it lies on OI. Okay. So what would be the best method to show they concur? Is it Trig-Cheva, normal Cheva's theorem? It almost looks like MN and P are like the midpoints of those, but it's not. I doubt that's true. Yeah, it's close in this picture at least, but it is not true. So like GHF is the incircle, right? So yeah, maybe we could do something with a homothety, like a homothety that takes the inner circle to the circumcircle.
Can you draw the perpendicular from A onto NP?
Yes. 1 second.
And the symmetric ones. I want to see where orthology center is.
Okay. Does it? Oh, I thought it passed through G for a second. No, that's not true. Okay, so let's see. So A to NP, B to MP, and C to NN. Let's see. So this is A to N.
If we can show that this intersection point is on IO, then we are done by Sondat's theorem. But
Oh,
of course,
Sondat's theorem.
yeah, but of course we have to prove that AM, B, and CP are concurrent.
Yeah. Interesting. Okay. So is it obvious that, how do we know that those concur? So the perpendicular from A to NP, B to MP, and C to MN.
Because M and P and ABC are orthologic with orthology center I. One of the center is I.
So we're using orthologic triangles. Okay, so should I leave point K there for now?
Yeah, you can hide other lines, just leaving K.
Okay. So hide those lines?
Yeah.
Or, yeah, I'll just leave K. So yeah, it's been a while since I've used orthologic triangles.
Can you check that if AK passes through a mixed linear tangent point?
Yes. So I can do that this way.
Actually, never mind.
Yeah,
Doesn't
there's
seem
no,
so.
yeah. Can we use Desargues' theorem? Let's see, that might be a little tricky because we don't know where A, B, and MN intersect. So yeah. I'm just trying to see if I can use trig Cheba. So because Fm over Me, well, we want sine FAM over sine EAM, and that's like Fm over EM, and then like I don't know if it's times or divided by AF over AE, but AF over AE, like we can get those ratios because these are all angle bisectors. So yeah, if we can, so I think it might be equivalent to showing that DM, FP, and EN are concurrent. Is that true?
Yeah, it's Cevian's theorem. If we prove it, then we will prove that AM, B, and CP are concurrent.
Okay. Oh, is that the net? You said the nested Cevian's theorem?
Was that name? I'm not sure of the name. Probably it is.
What was the name you said?
Cevian nest.
Cevian's nest. Yeah. All right. Yeah, so that seems a little bit more tractable. So yeah, Fm over Me. I'm just trying to think how we want to compute that. That would be like sine FIM over sine EIM, and then like times like FI over IE or something like that. But sine FIM over sine EIM is sine GIC over sine BIG. So maybe it just reduces to a calculation then, right? Yeah, I think so. I think I can prove that DM, FP, and EN are concurrent. So I think I know that AM, BN, and CP are concurrent. Does that kind of make sense? Because like FM, like we want to use Cheba's theorem to show that FM over ME times EP over PD times DN over NF equals 1. But FM over ME, it would be like sine of FIM over sine EIM times like FI over EI or something like that. And then, yeah. So I think from there you can prove that these concur. We just have to show it lies on OI. Okay. So should I draw the point of concurrence? Let's see. It's going to be that point. Spells kilo, K-I-L-O.
Does KG pass through AX center? Can you check it?
I have KG passes through the X center?
Yeah.
Let's see. Oh, does K lie on A? Is K the Jirgan point? I think it is. Yeah. Looks like K is the Jirgan point. That's really interesting. Oh, no, I don't think it is. If I draw a really tall, let me draw a really tall triangle and see if that's still true. Hmm. Wait, how did I define K? K is supposed to be the orthology center, right?
Yeah.
Oh, but wait, because this isn't, I didn't draw the incircle right. If I did, maybe it is. No. I don't understand why it looks like it lies on AG, but oh, I guess if I make it obtuse, then it's clear it doesn't lie on AG. Okay, it's just very close. Okay, so I'll check if it passes through the X center. Hold on one sec. Let's use the in-center X center level. So I just have to reflect I over that midpoint. That would be the X center. And we want to see if AK passes through that. No, it doesn't. It doesn't pass through the X center. In fact, did you say if AK, like AK couldn't pass through the X center because AI passes through the X center?
No, I said KG, but it doesn't also pass through. Okay.
Okay, it doesn't. All right. KG. Oh, looks like K lies on MN. It's hard to draw a good diagram, but I think that's good enough. So can we do anything with the homothety? Like I wonder the homothety that takes the inner circle to the circumcircle, does it take M and P to some special triangle? I'm not sure. right. So yeah, at the very least, I could write the first part of what we figured out, which is that these are concurrent. What do we know about the line IO? So yeah. So I'll be right back. All right. The only way I know to show if something lies on OI is by like some kind of homothety. I don't know any other easier way.
Can you name the intersection of AK with NP?
Okay. So D or HA, you said?
AK.
Oh, AK, sorry. So the feet of those altitudes.
Yeah.
It almost looks like these are isogonal. That would be interesting. Doesn't it? Doesn't it look like AK and AL are isogonal?
Yeah.
Let
Yeah.
me check that first. Although it's a small enough angle that it's no, it's not actually true. It looks very close, but all right. So, and you want me to draw the symmetric ones?
No, that's enough. Q is enough.
Okay. Why did I draw this whole line? Oh, just in case it doesn't intersect on the segment, I need to draw the line. Okay. Let's see, Q. What can we say about Q? So what's the theorem about the X center and EF? Is it like, I forgot what the theorem is.
Line connecting O and X center is perpendicular to EF.
Okay, that's the theorem. All right. Okay, so DEF and the triangle with the X centers are orthologic. That's kind of what the theorem is. Yeah. Should I add any of the mixed linear circles? Let's see. Maybe. Let's just try it. I was thinking. Because, yeah, OI. Yeah, I'm not sure where to go with this. You want to try it for like another 10 minutes, or what do you think?
We can do this problem a couple of minutes.
Okay. All right.
A reflects G on AI. Does AM pass through G prime?
Let's see. Oh yeah. That's really interesting.
I guess I saw this problem before or a similar one. I'm not sure.
Okay. So yeah, that's really interesting. So there's some lemma that says that so yeah, Chuan basically Serdar was saying that like I'm not sure how to prove it, but if you let AM intersect the circle, then that's actually like this reflection of G over AI, which is really interesting. I would not have expected that. If we know that,
If we know that, then G prime, H prime, and F, no, G prime, H prime, and J prime is similar to ABC.
okay. So let me draw those.
Not just similar, also homothetic. So we will be done.
That would solve the problem.
Yeah.
So yeah, that looks like it has to be the key to the problem. And you've seen that lemma proved before. So like, did you see, when you said you saw it before, did you see this problem before, or you saw this lemma before?
I saw a problem that uses this lemma, I think.
Okay,
I will look for it after we solve this one.
interesting.
Okay,
And
this is true by isogonal line lemma. If you can you intersect EF with BC?
okay, now it almost looks like Q and this are the same point, but oh well.
No, I'm not sure, but maybe we can use isogonal line lemma.
Hexagonal line lemma.
Yeah, if we prove that GAI equals to IAM, we are done.
Okay. BAI equals IAN, or sorry,
GAI equals to IA G prime.
oh, those angles. Okay. right, so yeah, we could try the isogonal line lemma. So that's why you let BG and okay, let me think how that would work. Okay, so we'd have like B, G, M, E, and we'd want to see how that works. So BG intersects ME at R, and then BE intersects MG at I. So we want to show that. Yeah, how does that work? Oh, I think we need to like. So if we like draw a point here, maybe it's the same as showing that SA. We had B, G, M, and E. We want to show RAB equals SAC. Is that the idea? Is that the same as showing these are perpendicular? Let me see. Because I think it might be trivial by the isogonal line lemma. Yeah, because like angle RAI is a right angle and AI is an angle bisector. So like angle RAB is equal to angle SAC, right? So if you use the isogonal line lemma on AB, AI, AM, AE, or sorry, no, AB, AG, AM, AE, then I think it solves the problem. Is that right?
But isogonal line lemma wasn't that, right?
Is what?
Isogonal line lemma says if you intersect BG, ME, and BMGE, can you
Yeah.
intersect BMGE?
So, oh, BM and GE, not GM and BE. Is that what you're saying?
Yeah, I guess it was
Okay.
like this.
Almost looks
Yeah,
like these three concur.
they must be. If they are concurrent, then we are done.
Okay.
Isogonal line lemma.
I don't know what I'm doing. Okay, so we have BM and GE, where E is the foot of the angle bisector. So yeah, we can hide a lot of stuff if you want. Because yeah, we're just saying BM, GE, and the perpendicular from A to AI for the external angle bisector are concurrent. You have to prove that. Wow, there's a lot of structure to this problem. Wondering if we can use like harmonics to show that those concur. All right, let's see. If I draw AG.
Can you draw AX center?
The AX center, sure.
I think trying to prove by using T is harder than the normal problem. So
Harder than the original problem. Should I delete
yeah,
T?
yeah, it will be better, I think.
Okay. And remove R or leave R?
I'm not sure. Maybe you can delete it. It's up to you.
All right, I'll leave it there for now. So draw the X center. Let's see.
On these website.
Oh, what? So that's the X center. It's a little bit far away, but it's okay. So I call it IA or something.
Can you also draw the reflection of S across O?
Cross O.
Yeah.
The top point of the circle. Those we know are collinear. Okay.
Can you also draw the intersection of S prime IA with circumcircle?
Okay. This point.
Yeah, AM passes through C, I think. Yeah, I think. Can you check it?
Yeah. Yes.
Yeah, I found the answer, and the picture that they drew is not complicated like.
Oh, really? Do you have another solution? Oh, are you saying you looked up the answer to the problem?
Yeah, I have looked it up. They're using a Cevian theorem and Steiner theorem.
Okay. So that's interesting. Maybe we have a different solution though. Do you know what Steiner's theorem is? I'm not sure. Yeah, I'm not sure.
Should I send you the answer, or we still thinking to figure out?
Let's think about it for like 5 more minutes, and then yeah. So yeah, let's see if we can solve it. Like yeah, we can, like, after the session. Yeah, you can send me a link to it, but yeah, while we're on the session, let's try to solve the problems. But yeah, thanks. So this is interesting. I've never seen this point T like this before.
It's a mixed linear circle, but tangent from outside.
Oh, it's the X mixed to linear tangent.
Yeah.
That's really interesting. So yeah, you construct it in a very similar way to the one for the in circle. So yeah, I think these properties are interesting. Like point T, I didn't know about. Using the idea that OIA is perpendicular to EF is really interesting. We have the Cevian's nest theorem. We have this theorem that AM meets the circle at the reflection of G over AI. So yeah, a lot of interesting theorems here. All right, 3 more minutes, and then I will move on to another problem. But yeah, I learned a lot here. All right, let's try another problem.
I think I am almost.
Okay.
I will almost solve the problem.
All right, I'll leave it.
Wait. Okay, I solved it. A little beshy, but not that much.
Okay.
We want to prove that the cross ratio GRBC equals to TS prime CB.
Okay, TS prime CB. And
Yes.
once we show that,
Because if we project it from A, F goes to B, E goes to C, and R goes to S prime, M goes to T.
okay. All right. So,
Let me write it in the chat.
all right. Yeah, I'll type out I'll type out the proof that these are concurrent. And then, yeah, you could type out the proof that second part of the proof. Okay, so by the Cevian's nest theorem, we have so GRBC, that's MEMREF, and TS prime CB. So what's the question mark? So if you project through,
We want to prove that, the question mark.
okay, so we want to show those are equal, because if they are equal, then then GRBC is equal to TS prime CB, and that means then what does that tell us? Like, let's say we knew those were all equal. What would the
Yeah. After that, if we pull the ratio. I don't know the term.
Oh,
If you use
polar.
A for harmonic bundle, from A, F goes to B, M goes to T, E goes to C, and R goes to S prime.
Okay, so it basically proves dilemma that A, M, and G prime. Okay, so ultimately
Yeah.
we're trying to show A, M, and G prime are linear. That's the idea. Okay.
We know that A, G prime, P are collinear, so we want to, if we prove that ratio, then it shows us A, M, T are collinear.
Okay. Interesting. Okay. And so we want to show those cross ratios are equal, MREF, and so you're going to show, like, if we do enough projections, we can get from one to the other.
Yeah, I will prove the ratio now. I am writing it.
Okay. Let me know if you need to see the figure. DMFP. And then FM over ME. We sine FIM over sine MIE. Times IF over IE. Equals sine CIG over sine BIG. Bisector theorem and some calculation. We can eventually show FM over ME times EP over PD times DN over NF equals 1. And that means that the M, FP, and EN concur at a point L. Concur, we'll just say concur. And that implies AM, BN, and CP concur at a point L. So that's the first part of this problem. And now we are getting into your part. So let S prime, so I'll write it like this. Let the X
Actually,
term,
we don't need Cevian nest, but it's okay. It's not a problem.
oh, there's a way to do it without it.
Yeah, actually, we showed After my lemma, after we showed, we will just use homothety to prove that these are concurrent on I/O.
Okay. So we still need the calculation that you did with the cross ratios, right?
Yeah.
Okay. Maybe I'll just say label the points as shown. All right, let me get rid of this for the time being. And so then we have those cross ratios. Table. G prime is the reflection of G over AI. And then this implies that A, M, and G prime are collinear. Collinear. And once we know that, this TC versus okay, so this is another calculation. TC.
No, it's an explanation actually. I used a lemma in the calculation.
Okay.
I wrote the proof of it.
All right. So we have A, M, and G prime are linear, and then a homothety at okay, because then we're saying so triangle G prime H prime J prime we're saying is homothetic to ABC.
Yeah,
is
sides
that
are parallel from angle chasing.
okay? By angle chasing, G prime H prime J prime is homothetic to ABC and similar. So to ABC, thus L lies on OI. All right, so there's a lot of stuff here. I'll probably reread some of this after the session, but this is a really, really cool proof. And yeah, Chuan, now that we solved it, yeah, I think, yeah, if you want, you can put on the Discord the other solution you saw. But yeah, so much stuff went into this, so I really like that. All right. So we were working on this problem before, and we didn't solve it. So we could either do this, or we could try one of these last two problems. What do you want to do?
New one would be nicer.
A new one. Okay. So we have a triangle and a circle O, and we draw a variable line through the orthocenter, and we see where it meets the circumcircle. Okay. let's see, I should draw a ray on a line. So we have P and Q. And then two lines through P and Q perpendicular to AP and AQ. Oh, I think I've seen this before. I forgot how to do it though. I think it had like a pretty elegant proof. We want to see where they meet BC. At M, but yeah, I'm not 100% sure. And then N. And prove that the line through P perpendicular to OM. So we need to draw the center. And the line through Q perpendicular to ON. So we can draw those two lines. And we want to show they meet on the circle. Okay. Oh, wait, is that, did I do something wrong here? Let's see. So we have a line meets at a P and Q. We have through P, a line through P. Did I hide something? Wait, we have a line through P perpendicular to, oh, I think I drew this wrong. So I drew the lines through A instead of through P and Q. I need to go all the way back. It's my bad. We want this line. So these two are going to meet on the circle, obviously, at the antipode of A. And we're saying they meet BC at M and N. So this is M, this is N. And then we still need to draw O. This is O. And OM and ON. And we want to show the perpendiculars to those. Let me make this look better. Perpendicular through P to OM and Q to ON. We want to show those meet on the circle. That's kind of interesting. Okay. Let's clean up some stuff. Actually, let me draw this point right here. So this point and the line through Q perpendicular to ON. Let me draw that. So let me move things around just a little bit. This point. So basically, yeah, E would be like the midpoint of PF, but let's see. All right. Oops. So I like that diagram. Yeah, we don't know that this F lies on the circle. We have to prove it. So that's kind of it's almost like an angle chase. Like, yeah, we want to show angle APE plus angle AQG is 180. So yeah, maybe I should just draw PE and QG so I don't trick myself.
Draw anti-Steiner point of PQ.
Yeah,
It is F probably.
it's probably F. Okay, let's see. It looks like it's probably true.
It's true. Okay. You
Yeah,
have to check for one line because the other one is reflection of H with respect to BC.
they all concur on the circle. Yeah, it's a known fact. Okay, so interesting. So we want to show that PE passes through the anti-Steiner point. Oh, but the thing is, are these lines like reflections? Okay.
Actually, we just need one of point P and Q.
We just need one of the points.
If we delete Q,
Okay.
does it affect anything?
So you're just saying let F be the anti-Steiner point of this line. And then we want to show that, because yeah, M is where, yeah, we just need to show that PE
You
passes
also
through F.
you
Yeah,
can also hide G and N.
yeah. Very interesting.
Can you draw AD?
Yes. I don't know if it's worth drawing. So, oops. H prime and P prime. Yeah. It's probably, I don't know if we want to draw this cyclic quad, so, because we want to use that this is a right angle, right? So maybe it would help to draw this. I don't know. But then we do a point D, so we do use it there. All right, let's see. Let me think. So it's the same as showing that angle PH. It's the same as showing that angle PHA equals angle AH prime F. There's a couple ways we could do this.
Can you draw EF? You can do it from reverse.
Yeah.
So we want to prove that angle AH prime F equals to AHP.
Right. Which is the same as saying, yeah, APF is AHP. We need to use it, that's right angle. You know this is parallel to BC, maybe that's helpful. But we need to use that M lies on BC. Which is, yeah, well, I think it might be good to draw this. I think we're pretty close. Is this tangent to the circle? No, not in that case. Yeah, I feel like we're close, but something's missing. So maybe it is worth drawing point Q. Just I'll just add it for a second, just that point, because angle PH or AHP is half of arcs AP and this arc. Let's see.
Okay, I solved it.
Okay.
If we prove the similarity, if P H prime H is similar to P H prime H is similar to O DM, then we are done by angle chasing, because OMD equals to PME, it equals to ADF, so it will be the reflection H prime F will be the reflection of HP across BC.
Did you say PME equals ADF?
We want, if we prove that angle PH H prime equals to OMD, then we are done.
Okay. All right.
Because OMD equals to PME, it equals to ADF, and it equals to AH prime P prime. So we will get PH H prime equals to P prime H prime H. So it will be the reflection.
Okay. And then, okay.
So prove that similarity, prove that triangle PH prime H is similar to ODM. We write ratio. We want to prove that HP over H prime H, sorry, H prime P over H prime H equals to DO over DM.
Okay.
We want to prove it. If we divide both sides by 2, then we want to prove that H prime P over H prime I equals to DA over DM. And this is true, because of the cyclicity of APIM.
Okay. So H prime P over H prime I equals H prime, equals DA over DM? Is that what it was?
We need that, and this is true because of this circle, APIM.
Okay. So trying to think about that. Okay. So I think he said H prime P, sorry, it's Karamba diagram, but H prime P, okay, we want to show H prime P over H prime H equals DO over DM. And if you divide H prime H by 2,
And multiply DO by 2.
okay, so H prime P over H prime H is equal to H prime P over 2HI. And then you have DO over DM, or DO over DM is equal to dA over dm over 2. Okay, that would be dA over 2 dm. Okay, so I don't need to put, I mean, it's understood, I guess. Then, so we're saying H prime P over HI is equal to, I'll say H prime I is equal to dA over dm. And that's true because angle PIA is equal to angle PMA. So, okay, I wonder if there's an easier way to think about this. Basically, we're saying there's like a spiral similarity. We're saying so triangle PIH prime is similar to triangle AMD. I think we're starting with that. So by spiral similarity, PIH prime is similar to AMD, right?
I think it's not spiral similarity, is it?
It's not really a spiral similarity. Okay, so
Because
by,
they are not oriented, they are reversed.
okay. So PIH prime is similar to AMD. We're using that a PIM is cyclic. And then we have that and that, and then PIH prime is similar to AMD. That means that H prime P over H prime I dm, that implies that H is equal to dO over dm, which means that so once we know those two are equal, then that means that those triangles you want to show are similar. So H prime PH similar to DOM. Okay. And then it's kind of an angle chase because angle PH H prime is MOD, which is, or sorry, OMD. So PHH prime is OMD. Which is PME. And PME is ADF. That's what you're saying, right? Which is angle AH prime P. So, but wait, okay, so that means that I'll just say 180 minus AH prime F, because we don't really know that these are collinear, right? Just so I don't confuse people. So that implies F is the anti-Steiner point of point pH. And once we know that, so by symmetry, F is the anti-Steiner point, or yeah, but by symmetry, by a symmetric argument, I'll say. And that solves the problem. Okay. All right. Very interesting. See how much time we have left. Just 10 more minutes, so we might be able to just peek at another problem. Let's see. Probably by the time we draw this one, it'll almost be over. We could just look at the one that we started and just finish with that. So, yeah, here is the problem we looked at before. So, yeah, we have a triangle ABC. We draw O and H. And then basically we draw the parallel. So I added in some points here. If you want, here's kind of what it looked like originally. We just draw a parallel through O to OH through D, and it meets at M and N. Oh, this problem is similar to the first one?
No, the one we first solved.
Okay.
The concurrence on IO. I posted a similar one. The concurrency point is the same, but the lines are different.
Interesting. Let's check it out. So this is like related to that problem.
Yeah, very related.
So let's see. We have, let me see if I can expand it here. We have a triangle ABC and center I and circumcenter O. AD, BE, and CF are the bisectors. MNP is the bipedal triangle. So it's a little bit different because it's the perpendiculars from I to each of these sides, right?
Yeah.
Interesting. Yeah, there's so many of these problems where like things concur on OI. It's really interesting. All right, so I'll go back to this. But yeah, there's really not, it's not as hard as it looks because I added a lot of stuff, but you draw the parallel to OH through D and you let it meet at M and N. You meet A, B, and AC at M and N. And then you draw the line DI, where I is like the midpoint of AE, and it meets at P and Q. And then if M, Q, and PN meet at T, you want to show DO and T are collinear. So I drew this. We can delete it. Looks like Leia is joining. So, hey Leia, we have about 7 minutes left. But oh, sorry. Hey, Leah, we have about 7 minutes left. I changed the time. I don't know if they do daylight savings time in your country, but like in the US, they set the clocks forward an hour. So I made it like an hour earlier. But yeah, thanks for hopping on for the last couple minutes. So yeah, so we solved, I think, 4 problems. And so this is one that we didn't solve yet. I think I added, let me get rid of everything I added. I don't think there was a point F. But yeah, I'll just leave F there. Do I need L? No, that was something I added. Do I need K? I don't think so. So yeah, this is like the original diagram. You have the parallel to OH through B, and it meets it at M and N. And then you draw a line DI, where I is the midpoint of AE, and it meets it at P and Q. And then MQ and PM meet at T, and you want to show DO and T are collinear. So looks kind of interesting. But yeah, the very first problem we solved using an interesting lemma from video 84B. So yeah, you can check that out after the session. All right. So yeah, what I saw when I was adding in those points, so I don't think we need K, but basically I constructed a parallelogram. So this point right here of intersection is actually the 9-point center. So it's the midpoint of OH. And that's, I'm trying to remember how I proved that. So yeah, somehow I showed OX. Oh yeah, by a homothety, OX is parallel to ID. So since D is the midpoint of HX, G is the midpoint of OH, and so G is the 9-point center of ABC. All right.
Is Geometry Mathly a journal?
I think it's a journal from Vietnam. So I think it's just these 2 years where they just focused on geometry. And then maybe in other years they did all kinds of math. So like yeah, like on this website I only see it for 2021 and 2011 and 2012. But there's a good number of problems, so I might do some on the next couple sessions. And then after that, yeah, I don't know. So I think I've done most of the rest of them before, but we could redo some of them because I don't remember. There's a lot that I didn't do and a lot that I just don't remember. So yeah, for this problem, I don't know if we want to use the Sarg's theorem or yeah, I'm not sure what the best idea is. But yeah, Vietnam always has the best math problems. for the best geometry problems. I can't say, I don't know if I can say math in general, but yeah.
Can you also name the intersection of Mn with AE?
Yes. I wonder if XE is no. All right, so I think I'm gonna stop here. So thanks a lot for participating and giving us enough to make a video. This was a lot of fun. So yeah, I appreciate the time you spent to come on and work through the problems.
I think I might be close. I'm not sure. Can I say
Okay.
something?
All
Can
right.
you intersect also DO with AC?
Okay.
Also assume that ED at AC at a different point K prime. I will prove that AQ AK QN is harmonic. So we will be done.
Okay.
K will be equals, K will be same as K prime.
Okay. So AK prime QN you're showing is harmonic.
If we say K prime is the intersection of TD and AC, we know that AK prime QN is harmonic. And now I will prove that AK QN is harmonic.
Okay.
If you if you take harmonic bundle HGOJ from D onto AC, it's obvious.
So HGOJ, did you say?
Yeah, from D onto AC.
Okay. And that is harmonic, HGOJ. How do we know that HGOJ is harmonic from D?
J is parallel to HO and B is the prime midpoint of
Okay.
OH.
So yeah, that proves it. You did it. Yeah, I had no idea it was that easy. That's great. Yeah, I might as well type it because it's not really a long proof. So, HO G and HO infinity is equal to -1, and then projecting through D, then we have AKQN is harmonic. And that basically, so I use that G is the midpoint of HO because HD equals DX, and so by homothety, DI is parallel to XO. So I did use that for that. And then we have HD equals DX implies HG equals GO. And so then we have this, and then this, and then I'll just say This implies that T, D, and O are collinear. Because yeah, I know it's kind of like the converse of it, but all right. So yeah, that was easier than I realized. All right, so yeah, thanks for participating, and everyone watching. Thanks for watching. If you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again, and have a great day.